They don't name this. I looked at Churchill and Brown book. They don't even name this one, but I'd like to name this one. The fundamental theorem of complex integration. Part 2. If you took calculus in Armstrong, we used to use the Stewart's book. It's a wonderful book, and it separates fundamental theorem of calculus in two parts, part 1 and part 2. So it's analogous to that. We have any region R. R is just any region. And we happen to have, it's really a human thing in it. We happen to have this precious function fz such that if we have this one, if you complex differentiate this function we have, it becomes the function we're staring at in the integral. Okay? I actually did not name this function ever before. So what is a good calculus name for this fz, capital Fz? This is blank of little fz. Integral is not a very good word. Antiderivative is the best to describe what the nature of this thing is. And this part I'd like to write in red is really important. If you miss this one, you will trap into all the things that I'm putting out there. It's a problem in this course. If this part is not so important in real value calculus, but here is the utmost importance of this whole discussion. All right? So make sure that we're not just looking at a formula here, formula that works on R. That's the important part. Okay? So if you have that, it's all about this complex integration, right? And this one becomes, if you have that, that works the entire region. It doesn't matter if it's multiply connected or simply connected. It's f of z2 minus f of z1, where gamma is going from z1 to z2, if that's gamma. All right. It looks a lot like a fundamental theorem of what? Fundamental theorem of line integral of what? Vector fields, right? That you learn in Calc 3. It looks just like that. And instead of f, that was a potential function back then, right? But it's the same thing in the context of a complex function. If you really strip this one into real part and imaginary part, that's exactly what's going on. Okay? And what is the most important part of this to pay attention to in this part of the theorem? What is that? You must have this antiderivative that's defined on everywhere in this region, multiply connected or not, everywhere. Okay? So let's look at examples. We're going to look at the two sides of this problem. Well, before I look at an example, I have something to remind you of. This little remark, I've already said that before, but this is the right time to talk about it again. So we have complex function and ddz, and we know the meaning of this one, right? And we have very difficult, I had gone through very lengthy introduction of this one. And when you go through the definition of this one, a denominator of the difference of quotient of difference is a complex number, right? So in this process, you looked at the Jacobian variety and look at all that, tangent vectors. Final bit was rotating back of its own angle. Remember that part? So that's a weird part of this one, this definition. Denominator is not denominated by scalar. It's a complex number. The complex geometry in the denominator involve two things, scaling and rotating back, versus ddt of gt, g of z. This makes perfect sense, but we need a little bit of explanation about this one. How do you make sense out of this? This only makes sense when z is parametrized, right? and then t is a real valued. So when you go through this, you have a denominator in that limit calculation. You don't have complex numbers. It's just a usual real separated thing. So what really happened, this one, is really the chain rule. G prime of z, which is this one over there, multiplied by what? Chain rule. dz dt, z prime exactly. Things that we do in complex integration, right? Something here multiplied by dz dt. So understand this meaning of these two things, okay? And then we can explain this one nicely. But first, example, R is this thing that we looked at a lot, c minus 0. It's not 0 comma 0. This time is whole complex number, and 0 is a complex number removed, right? And we have this integration, and c is the curve z equals e to the it, where t going from 0 to 2 pi. Then we have a meaning of this 1 over z dz in there. Correct? And we can calculate this one directly, and then what was the answer? Anybody remember the answer of this one? One over z and going around unit circle one time, that was a 2 pi I. Okay? Alright, what about this one? Can we find the antiderivative of this guy here, right? So that this one is a simply difference of the values of the two antiderivatives, right? Okay, who wants to go for antiderivative of that? So book uses this notation, integral without path or contour, 1 over z and dz. For antiderivative, this is the indefinite integral symbol we use in calculus 2, right? So we're going to use this notation. But make a clear distinction, the meaning between this one and that one, right? It's a complicated concept in here. It's a relatively simple concept, right? So who wants to go for this one? Antiderivative of 1 over z? Log. Which log are you going to choose? Principal log, right? Principal log. That's one idea, z. But there could be a bunch of constant you can add. And even if it is not a principal log, it's all about 2 pi ki, 2 pi ik, whatever, right? So they're all constants. Constant. So this kind of covers all, none of them. So we have, do you think we have antiderivative that is defined on R? Which is analytic on R? That's what we... This one has some famous thing in there. This one has some problems. It's not even defined at 0, but that's okay. We remove the 0 there, right? But it has something. What was that called? Branch cut, right? There, in that branch cut, the values jumped abruptly. There's no point of discussing continuity at all. So here's what was the branch cut. And here's that's a 0. And that was this line right there. Negative real x's. What was the value at here? Log value. Whatever the real part plus argument of that angle, right? Arg z. Remember that? Arg z. What's the argument there for standard principal log? Pi. What about point right below there? What is the log value there? Whatever the real part plus I times negative pi. So, the function values are change all of a sudden right in that neighborhood, right? Not continuous. No point of discussing analytic property at all, right? Therefore, have we found an antiderivative that works on entire R? No. Therefore, you cannot apply this one to that. Okay? But if you have 1 over z squared dz, right? And sure, you can just put this one in. It was actually one of the Homo problem we just went over, Homo 1 3.4, right? but we have a now different way of looking at it. Let's try it again. I don't know the answer to this one. We know the answer to that. We actually worked it out. It was a 0 before. Okay, so you actually use definition and directly, and then you have 0 right there. Make sense? But let's use this idea. Do we have an antiderivative of 1 over z squared dz? Let me give you a better form. Z to the negative 2 dz. Somebody do this one? Think of you were tutoring some Calc 1 students and right in the tutor center. What would that be? It was a negative 1 over z, right? Whatever the, x to the alpha rule, the antiderivative, x to the n rule. So you get plus c. So you got some antiderivative? Is this guy defined everywhere on R? Does this one have a branch cut? The only thing that has branch cut in the class of elementary function is log. Since it's not really involving log, where is this thing is not defined? Denominator 0 is equal. That's the only one. So here, it's okay. This guy is actually analytic on every way except a 0. It does not have this weird branch cut. So this theorem is applied, right? Correct? So what is it? Therefore, by fundamental theorem of complex integration, this 1 over z squared dz over that contour, circle C is, what is it? Negative 1 over z, evaluated where and where? Initial point and terminal point. It's familiar territory that you've done calculus all the time, right? That's exactly what that is, right? Yeah. So what do you know about z1 and z2? It's a circle, starts in here and coming back there. So aren't they the same? So it's because of that, it's a 0. Okay? So you're going to practice this weekend thinking about antiderivative of complex function, not mechanically. What do you always think about? Most important distinction here you have to make here. Is this defined on the entire region we are playing with? Right? And then you'll be able to distinct when do we use this one, when do we not use this one, and things like that. Okay? One more thing, and then I'll let you go. So that's an important example. Back to 1 over z again. Back to 1 over z. Alright, we're integrating a complete circle around it, right? So here's a different point of view. This complex plane. What if I do just like this? Alright? So the circle connects these two things, right? So I'm going to call that one z1 and that one z2. So going around this circle path, I'm going to call it the gamma. So go around the gamma, 1 over z dz is going to be so this path it lives inside a nice region that so let me try it like this. If I think about this region right there that successfully avoid this branch cut, and this doesn't matter how close these 2 points are, they're inside this region, outside in the region in here. Is that alright? So I'm going to call that region R. Okay? Then 1 over z, antiderivative of this one, z is log z, works on where? Entire R that is missing that part. Is that correct? Right. So it's going to work. Correct? We have R and everything is analytic. So what is the answer here? Log z. You can use any antiderivative. This constant will cancel out as you take the difference. What is the value anywhere? z1 and z2. Is that right? Okay. So log z2 minus log z1. You have to make sense out of this part in here, the missing part here, that'll complete the integration, right? This missing part, as this one getting shorter and shorter, you have to show that that integration is negligible, which is not trivial at all. You have to do some calculation. Okay? But if that's so, then limit of this one will correctly predict this value, right? So I'm going to call that slit right there gamma 0. So here's a statement. If this integral gamma 0 1 over dz approaches 0 as zn, z2, z1 and z2 are approaching to each other. It is, nobody uses notation, but it makes sense, right? Z1 and Z2 are approaching each other on that circle, and if you have that notation, you know that gamma 1 over z dz is going to approach our original target. What is that target? The circle 1 over z dz, right? Does this plan make sense? That part's missing there, but as we get smaller and smaller, if that missing part approaches 0, and the remaining part will approach the entire integral. Part make sense? Yeah. So, and you have to see this one. And what happens if this z1 and z2 are close to each other? This is exactly log z2 minus log z1. It's a real part subtracted and argument part subtracted. Is that right? Real part of the first one, argument part, imaginary part subtracted like this. Real part is the length of these two things. They're all heading to the same position right there, which is -1. So what do you think about this thing? Where do they go? Length of z2 is almost +1. Length of z1 is almost +1. So it's a 0, right? But here, this guy is causing the problem, the branch cut, right? They're not going to the same place. Where's this one going? Z2, argument of z2. Almost a pi. And what about argument of z1? Underneath it is a -pi. So where do they go together? 2 pi I. This thing actually explains the entire phenomenon. What is really going on? Not like some slick formulas and some fancy theorem. Boom, here is a 2 pi. Is wonderful and, elegant and beautiful. But this really explains what on earth is going on and behind it all these fancy formulas. Is that right? Okay, that's it. So we're going to do